Hey guys, today we are going to discuss ideation. So our producer at Kado is Jagannath. Jagannath, welcome.
Glad to be here. If you have a high level flow of tasks, the next step would be to turn that into methods. At Cardo, we show you how to create that high level flow of tasks and then turn them into methods. Let's get started. In the last one, we talked about ideation. Our focus for smart buildings was on surveillance and incident response. This was the flow we developed. Okay, we started with the end, with the preventive security engine, and we worked back step by step all the way to the inputs, right? And we showed how these different things are interconnected, what they do, and so on. But we discussed it from a standpoint of the task and what it does. We touched upon the methods and that a little bit, okay, but we didn't get too much into the detail of that. So now in this video, what we're going to do is we're going to go step by step. So we're going to start with feature extraction and then building modeling, and we're going to work from 1 2 all the way up to the last one, which is the preventive security engine. And we're going to get into the details of the methods, how they're trained, what data is going to be used, and so on. So it's a little bit more flesh on top of the bone to see how all this could potentially come together. Okay. So the first step is feature extraction. As you can see, it's a preparation step. It's a data prep step for step 8, which is surveillance, and that's how we're going to approach it. So let's get into that. It has two parts. Okay, the first part is actually extracting the features, and the second part is storing it in some sort of information system or database as a knowledge representation. The first part has a couple of options. One is a classical computer vision based approach, and the second is a learning based approach. We have talked about this before. The machine learning approach for facial recognition is a best practice approach. There's tons of models that do that. Our problem is slightly different. We're not just talking about recognizing faces of individuals. We also need to do that in a crowd, in a restricted area, and we need to do that with very high fidelity and trust. We cannot have too many false positives or negatives in this process. Towards that effect, we wanted to use biometrics in order to simplify the representation and improve trust in the model. So that's the background to this. So with that in mind, there's again two options for feature extraction. The first one is learning based. You could mine the database of access control. Now these are available in every building. Usually when you go to the building and you need access to a restricted area, you go to the security office, you get your picture taken in a lighted environment, it goes on an ID card, and the ID card has some sort of chip that lets you into that area and so on. Right now, that information, right, those images, you want to mine them, okay, and you want to turn them into the most important features, and you want to store that. That could be the learning approach. Okay, the computer vision approach takes a slightly different tack. It uses morphometrics. The morphometrics are things that you may have seen on TV or in other places where you have like geometrical shapes describing a complex contour like a face. You might see lines, you might see curves, right? You might see like symmetric curves, lines, radial lines, stuff like that. But they come together to describe the key features of that particular contour, and in this case, a face. Okay, that sort of representation simplifies the face, right? And training a machine learning model could potentially be simpler because of the more condensed representation that we have. And that's for the subsequent step. For this step, though, this option would require you to run that computer vision algorithm to extract morphometrics and then store that in the information system or the database. Our option at Caro for this particular problem is option 2. for the reasons that I've mentioned before. Okay, so that's feature extraction. Let's go to the next one, which is building modeling. One of the things we saw when we were talking about the high level flow, right? Then this is necessary both to create the cloud model, which was step 6, as well as the preventive security engine, which is the final objective, is that both of these need a logical representation of the building. So spaces and how they're connected. So that's what this step does. Okay. Again, there's two parts. One is you need to do the representation, and then you need to store that in some sort of an information system or database. So this information, like the data, building data, is available in the BIM system, the Building Information Management System. Blueprints and floor plans, you mine these, right? This could be in different formats. There's different standards, and this is like a best practice in building management. You extract that, you mine that, and then you turn that into a graph. So there's different options here as well. The simplest option is just a graph of spaces and how they're connected, nodes and edges. Very simple, okay? And you put that in the graph database. Option 2 could be you could maybe potentially add some metadata explaining each one. So if this is a floor, if it's a particular room, it could be a corridor, just giving some information about which floor, which room, right, what it's used for, and so on and so forth. So that's just enriching the graph with metadata. That could be a reasonably feasible option. Option 3 takes it one step further. It says that all the different classes in a building, okay, could be the type of room, it could be a type of corridor, it could be a type of metadata, okay, of these things. All these things you want to build a structure of classes and their interrelationships, and that is an ontology. Okay, an ontology lets you define meaning formally and potentially do logical reasoning. So it's a slightly more complex version of just a graph that's enriched with metadata. Okay, so that's option 3. Now, option 4 is something that's takes you in a different direction. Here you use a solver, okay, a search or a planning algorithm to model exit paths or I don't know, pedestrian paths. You can model route density, right? You can model things like that, and these assist in incident response, in taking actions. So if you want to, for example, model the best, the fastest, most efficient routes just on a day-to-day basis for people to walk through the building, and just maybe change the layout a little bit or use signage to help with that, this kind of an approach or a model would help with that. If you want to model on the fly, if there's an incident, like for example a fire drill or an actual emergency, then in terms of exiting the building and working with that, you need exit paths, and the solver could help with that based on real-time information. Okay, so that's option 4, and these are the different options that you have. The one that does the least is option 1, and it could be feasible for both step 6 and step 9. Okay, if you don't do the solver in this step, then you'll need to do that in step 6, as well as you need that information for step 9. So it depends on where you perform the pathfinding. Okay, if you do it here, then you don't need to repeat it for steps 6 and 9. So that's building modeling. So the next step is extracting and modeling regulations. Okay, laws and guidelines and rules and regulations are usually available in a digitized form. Okay, so this step has 2 parts. Firstly, you want to mine that. So there's some sort of a natural language processing approach, usually machine learning based. Okay, once you extract that information, okay, you want to store it in the form of an ontology, right? And this could be done using expert knowledge, and you would do it like an expert system, but you're basically capturing the expertise of a human person, right? And so you combine these 2 approaches, where you've got a human in the loop giving the guidance and working with an NLP algorithm, right? There's also a part where incident response. So how to respond in some situations based on what goes on. And this is a basically probabilistic process. So some sort of probabilistic reasoning. The old word for that was fuzzy logic, but some sort of a probabilistic reasoning and modeling approach for those situations where judgment and uncertainty are inherent. Okay, so you have these steps, and then once you do this, you want to store it in some sort of a representation. Could be an expert system or an ontology, but that's the output of this. So we talked about expert systems, we talked about ontologies, we talked about NLP. How do these come together? The first option is just to handcraft an ontology using the rules and guidelines. Okay, this would be laborious, but if you have a project for multiple buildings, you probably just need to do this one time, because rules and regulations don't really change across different buildings in that sense. Okay. Now, the other option is to use natural language processing as a filter or as a starting point, and then take the output of that and then pass that output to the human expert in the loop to then fine tune the ontology. So that's also possible. So the natural language processing approach by itself is not 100% reliable. Okay, you're gonna mess up the representation. So the hybrid option, where you have both of them working together, might probably be the best way to go. But then the output of all of this is ultimately the ontology. Okay, that's the step of regulation extraction. This ontology or knowledge base serves as the repository of or guidelines for step 9 during incident response. Next up, we've got person detection. Okay, this one is fairly straightforward. You've got video feeds, CCTV, in the common areas and the restricted areas. Okay, you combine these two things and you just create a person detector. It's fairly straightforward. So a couple of options here. You are using computer vision here. The simplest way is to just say that there is movement and just detect that, right? You can just say that if the pixels change, then there is movement. That lets you know that maybe there's a person in the area. Something more sophisticated than that, you still want to be able to tell the difference between, is it a stroller, is it a baby, is it maybe a pet, maybe it's an object, or maybe it's a person. And you want to be able to differentiate that. That might be the option that we go with for this problem. Now, once you've done that, okay, the next step would be to identify the pose, right? So the person detector feeds the pose identifier. This is also a machine learning step, okay? Whereas with step 4, we relied more on traditional computer vision techniques. With step 5, we are probably going to be very heavily machine learning or deep learning based in this situation. There's two options here. Okay, the first one is to sort of estimate or build up a stick figure. So you're talking about detecting the joints, you're talking about connecting them to create a skeleton, and then you're talking about characterizing the pose of the skeleton. Okay, and you've seen skeletal stick figures drawn around people. It's used heavily in computer games, like in gaming. It's used in special effects. You may have seen it in on articles or videos, but the first option is to draw that stick figure and use that in your machine learning process. The second approach is to just directly use historical data, okay, and estimate the pose of an individual holistically just using machine learning as a black box. Now, this is also potentially feasible. The first one gives you a little bit more information. It's enriched. We prefer that option for this. For either option, you're still using a machine learning or a deep learning model to do the work. Okay, next up is the crowd model. This is an important step in the overall architecture because it feeds a lot of the subsequent, actually every subsequent step requires the output of this, right? You've got two parts. One is a simulation, and the other is a solver. And crowd modeling is a great example of how two different families of methods can come together and how their synergies work together to model something that's much bigger than just the parts themselves. Okay, so there's two parts, like I said. One's a solver, and for the solver, right? So your building model is going to provide the logical representation of spaces and how they're connected. The building model could also potentially provide paths, like we discussed, and if it doesn't, the solver does that job, right? For example, if a person has to visit two stores out of 100, okay, and the number of ways in which you do that is 100 times 99. So let's say that the person is going to visit, say, one out of the 100 stores, okay, and then for the next one, they're not going to visit the one they already just visited. So they're going to visit any of the remaining 99. So the number of different ways is 9900. But that's just the total possible combinations in which a person can visit two stores out of 100 in a mall, right? That's not going to be the case in reality. You know that there are some stores that are going to be more visited than others. Okay, even if you have that information, you can sort of model that using the solver. If you know that a person, if, for example, in an agent-based simulation, that a person is going to visit these exact three stores, and you know that across 100 people, you can then plan the pathways and the most efficient way in which these 100 people visit those sets of stores that they do in a given amount of time. Okay, so that's something that you can do using a solver as well. But that is going to be like the first step. If the building model provide paths, you need to enrich them using some information depending on the simulation you're running. If the building model does not provide those paths, then you need to create them in the step, and that's the first part. The second part is the simulation. Okay, there's two options to that. One is the discrete event simulation. A discrete event simulation is basically treating this problem as a random walk. So you're saying that there's a 30% chance that the person enters from this entry. There's I don't know, a 1% chance they visit a particular store, and then there's a 5% chance that they're going to stop by and get a coffee, and then there's a 2% chance they're going to visit the food court, and that maybe an 8% chance they go to the movie theater, and so on. So everything is modeled as probabilities, okay? And it doesn't necessarily take into account things like the spaces. It doesn't take into account bottlenecks. It's more a logical representation in that sense. Even if it doesn't do that, it can sometimes produce quite remarkably accurate models of how facilities work. Okay. The other option is to take these things into account. And the other option is to consider individuals as agents that have objectives. So it's not necessarily just probabilistic that the person has an 8% chance of going to a movie theater. People go to facilities with objectives in mind. They either want to browse, they have specific things that they want to buy in the shopping list, and they may want to go pick up a cup of coffee. They might have the intention of going to a restaurant, right? All of these things. So that is called an agent-based simulation. So it considers individuals as agents and objectives. It models spaces and spatial constraints. It models bottlenecks. So it's a little bit more realistic in that sense. Our approach to smart buildings, okay, is that in step 6, we're going to do discrete event simulations. But in step 7, which is the next step, we're going to model that as an agent-based simulation. Okay, and so we'll see that in the subsequent step. So here, step 6, again, there's two parts to it. One is the solver either creating the paths or enriching them based on the simulation you're running. And then the next part is the simulation, which is either a discrete event simulation or an agent-based simulation. And we are choosing to run a discrete event simulation in step 6. Okay, so the next step is behavior modeling. In step 6, you obtain the crowd model. Okay, so you do that through a simulation, and it uses a solver to get paths. Now, the output of step 7 ultimately is you want to be able to characterize suspicious activity in restricted areas. Ultimately, that's our goal. You may also want to know cloud activity in any area, regardless of type, in the event of an emergency or a fire drill or maybe an occasion and stuff like that. That's also a secondary objective. Okay, so the way you approach this, right, is that you want to be able to model individuals as agents. You want to say that they have particular objectives, which means that if there's a certain type of activity that they do. So the bodies move a certain way, they interact with one another in a certain way, right? Then you know that that is something potentially suspicious or dodgy about the situation. And this is why the post identifier serves as input to the agent-based simulation, and it augments what the crowd model creates. That's what you do in the agent-based simulation. A simple one would just be, let's just set these up as agents and do a planning algorithm and just create the simulation like that. But that doesn't really interact with the environment. It just considers that as an end-to-end planning episode. The more advanced option would be to throw in uncertainty into the environment. So maybe there's an elevator that stopped working, right, on the fly, or a restaurant offers up a special and a queue suddenly forms, right? Stuff like that. So there's things that could happen interactively inside a facility, and we also build models for how the agents or the individuals respond to that. Okay? Regardless of how you go with, okay, you still want to use machine learning to take that simulation as an input and then characterize that crowd activity as whether it's normal or it's suspicious, or maybe there is a theft, maybe there's an emergency. It needs to be able to look at the crowd behavior, and it needs to classify that based on the situation. And obviously, it creates a confidence score for how sure it is that a particular scenario is happening. Okay, so the next step is surveillance. We talked about this before. Step one, which is feature extraction, exists to feed the surveillance process. The crowd model also acts as an input, and you have video streams and access control information coming in, especially from the restricted areas, but also the common areas, and that all of these feed the surveillance model, right? There's one particular nuance here that needs to be talked about for access control, right? When you walk into a building to get your picture ID taken, right, it's done with you facing the camera directly in perfect lighting conditions. Okay, so the quality of the features in those images are going to be high, whether it's just machine learning based or morphometric. The same cannot be said of what you find in surveillance. Usually, it's going to be at an angle, the faces. You might not get the full face, right? There might be lighting problems. Going to be occlusion. They might be wearing a hat or some sort of facial gear. All these things can potentially interfere with the quality of what you get, of what you extract from the video feeds. Ultimately, it's a problem of taking what you extract and comparing that to the features that are obtained in step one. Okay, so there's two ways to model this. The first one would be machine learning based. So it won't be a single machine learning model, because you have the crowd input, you have the video feed input. Okay, you're going to need to first segment objects in the crowd, in the video feeds using the crowd data, recognize individuals. You're going to need to recognize faces, and then you're going to need to say whether or not this person has access in that area and they should belong. So there's lots of individual pieces that need to be built if you're doing the machine learning approach. The same thing is true of the morphometrics approach, which, by the way, is our choice for this problem. Okay, with that approach, you're still training a machine learning model. So what you're doing is you're training the machine learning model to extract morphometrics from faces. You still need to segment the objects. You need to recognize individuals and the faces. Okay, and then the machine learning model gets the best morphometric representation from the face. And then what you do is you compare the morphometric representation that you get from the machine learning model, correct it for perspective and occlusion and all these different problems that you have. And then the resulting morphometrics, you compare that to those obtained in the feature extraction. You can do a simple distance metric or some sort of a nearest neighborhood approach to do that. Okay, any metric, any distance metric would do. In that case, you have different chances of this being, I don't know, 4 or 5 different individuals, and then you rank them by the probability, and then say that it could be Joe with 70%, or it could be Thomas with 30%, or it could be Paula with 10%. So it could be any of these different individuals, and you rank it like that. So that way, it's a matter of taking what the morphometrics that come out of the machine learning model and comparing that with the morphometrics you obtain from the access control database. The second approach is easier because you don't need to retrain the model every time an individual's access control changes. Okay. All you're doing is training it to recognize an individual in a crowd, or all the individuals in a crowd, get their faces, and obtain the morphometrics and correct them for perspective and occlusion. Okay. That can be done across a host of individuals. And once it does that, you're now just taking the morphometrics that's obtained in the access database and you're doing a comparison, right? There is no retraining here that's involved. Whereas with the machine learning approach, that is retraining because the feature extraction process is going to change every time that the access control changes. And the machine learning model also has to change because it uses those features. Okay, so steps 1 and 8 will need to be done every single time, every night that a new person is added to that location or a person is removed. So that's the approach for step 8. Our choice is to use the morphometric approach and use learning to learn the morphometrics. So that said, the output of this is a person in that area, okay, and is a person supposed to be in the area or not. So that's kind of the output of this. Once you do the comparison, you have the access control, and then you know whether or not this individual is supposed to be in that area. And this information ultimately feeds the preventive security engine. And finally, we get to step 9, where all of these different things come together to solve or to address the end goal, surveillance and incident response. Okay, surveillance is the bulk of it is handled in step 8, but the preventive security engine is the one that takes the actions based on violations. Okay, so that's our end goal. It's primarily a solver. Okay, there's 2 types of solvers, 2 types of things that's going on. Firstly, there's logical programming based on different situations. Crowd model, crowd behavior. Okay, that's the behavior model. Output from the surveillance. Okay, it knows. Okay, so maybe there's a person that's not there in a particular area, and we need to do something about this. And we know that there's a crowd in the area, and in spite of that, we have this information. And so that's a logical programming. That's just rules and regulations and procedures that are enacted upon a particular incident. Okay. At the same time, there could be an emergency. Okay, so there could be an intruder during an emergency. It sounds like the plot of a Hollywood movie, but it's true. It could happen in real life, but different things superimposed. At that point, the search and planning mechanism kicks into action. It's also part of the solver. Okay, and now it knows how to react to the environment and maybe provide paths. So it does 2 jobs, right? One is it provides safe exit routes to facilitate that emergency or maybe that event. Okay, while restricting the intruders and making sure that either the places are locked down or they are quarantined in a safe zone for future action. Okay, so that's more like interactive order planning. So these 2 things are performed by the solver. The one thing to call out, right, is that the way to implement this, okay, you could just create this as rules in some sort of a logical programming approach. The old days, like when the days of the expert systems, we had languages like Prolog and Lisp. Some of them are still in use. Okay, surprising that those things are still around and it's still in many situations where it actually works. Some GPS systems use it, for example, but there are more current versions of languages that support these operations as well. So you could use them. Okay. Now, so that's just your logical programming for reacting to some incidents. But if emergencies happen and you have something going on, then you need partial order planning. If in step 2 your building model does not have paths, then this step has to create them. Okay, so we saw this, right? Step 6 and 9. Okay, if the building model does not do solving, then these two steps have to do it. It again depends on the complexity of the problem. If it's a very simple thing, then you can do, or you can get away with doing everything manually. You may not even need a solver. For very, very complex problems and many modern facilities, right, you do. And so it might just behoove you to do some of the pre-processing in step 2 and just do the step-specific enhancements in step 6 and step 9 based on what's needed. Okay. Yeah, so that's basically how the preventive security engine works. It's got two parts to it. One's just logical programming for incidents that are known upfront, okay, and the other one's an order planner, partial order planner, based on things that are emerging. So that's step 9. Let's look at the overall picture. Okay, there's a lot going on in this diagram, but you can see, right? Each step has been replaced by methods that we want to implement. And this intermediate step is very important because in the next stage, we're going to replace each of these boxes by the specific techniques that we want to run for each method. Now, for example, like I said, with steps 1 and 8, you could combine them together and have a machine learning pipeline that just does all of that. Okay. And that's the beauty of this kind of intermediate approach is you can do what ifs. You can say, I want to combine steps 1 and 8 with a single step. Or if situation is complex, then you want to run planning in step 2. If not, you can just get away with doing something simple in step 6 or step 9. This kind of what ifs and prioritization and trade-offs, this intermediate step of crafting the methods flow does that for you. In the next part, we're going to take this as input and come up with a technique flow for each one. And once you get the technique flow, it's time to develop it. At that point, it's prototyping and assembly, and those are steps we'll see down the line.
Okay, thank you, Jack, for the explanation and all the knowledge that you shared today. Thank you guys for watching. If you liked this video, please don't hesitate to like and share. And also, you can find our website just below. And you can also take the Hero method test to see how we can help you with all of this. So thank you again, and see you next time. Ciao.
Bye-bye.